Hello, and welcome back to a video series on MAC 1105 College Algebra. My name's Sean Perry. These are guided notes number 28 in the series, a review for the final exam. Question number 1 asks us to solve this equation. Even though this one has a couple of quotient bars in it, it's still a linear equation. But even if it were a rational equation and there were variables in the bottom, I would still start by proceeding the same way. We can always get rid of the fractions by multiplying on both sides by the denominators. If I take this 2 and multiply it up here, I'll cancel the 2's, and so I want to do that on both sides for balance. Likewise, if I multiply by 7, I will cancel these 7's, and so I want to do that on both sides. Once that cancellation to 1 is done, we'll have the following. We then want to get rid of these parentheses by distributing. If we multiply the 2 and the 7 inside, we get, which is now more obviously a linear equation, two lines that equal to each other. So we solve this by first grouping our x's to one side. I can move this 2x to the other side by subtracting it, which would cancel on this side to 0, and just leave me with 5x on this right-hand side here. If I move my x's from left to right, I want to move my numbers from right to left, so I'm going to subtract 21 from both sides. That cancels to 0 here, and leaves me with minus 31 on the left-hand side. All that's left next to my x is multiplication by 5, so I'll divide by 5 to get rid of that, and I'll do it on both sides. That cancels to 1 here, and so we just have x on the right-hand side, and on the left-hand side we have negative 31 over 5, which is answer A. Question number 2 asks us to solve a very similar equation. You should pause the video and attempt each one of these before watching me do it to try to figure out what you don't know in preparation for the test. So give number 2 a shot, and then let's see how you did. So just like before, we see these fractions, these long fraction bars in here, and what we're going to want to do is get rid of the fractional quality of this by multiplying on both sides by the denominators. If I multiply by the denominators, like 4 and 5, I will cancel what's in the bottom. But I can't just do that wherever I like. I have to make sure if I multiply by 4 on this side, I do it on this side. And if I multiply by 5 on this side, I've done it on this side. So that's keeping things balanced. We would then wind up with 4 times x minus 8 on the left-hand side and 5 times x plus 1 on the right-hand side. We distribute to get this line here, and then we group like terms by moving our x's from left to right. And if we move our x's from left to right, we're going to want to move our numbers from right to left. So we'll minus 5 from over here and minus it from over here as well. This cancels to 0, and this gives me minus 37. 5x's minus 4x's is just a single x, and so we're done. And that is indeed answer D. Questions 3 and 4 are asking for us to do some multiplication of complex numbers. We should recall that in order to multiply complex numbers, we really need to either distribute or FOIL, and then keep in mind that I squared is going to be minus 1. So FOILing here would mean multiplying a by c, and also bi and di, which will give me ac plus bd I squared. And you'll see why I grouped these this way in just a moment, but here we would also have an ADI and a BCI. All of these terms, all 4 of them, are going to be necessary to get the right answer, but as we said here, I squared is negative 1, so we can also write this in the following way, where now it's clear what are the real and imaginary parts of this complex product. So how would that relate to, for example, problem 3? First, I think it would be prudent to write this as a complex number 8 plus 5i times itself, so we can clearly see all 4 terms in our product. Then I would multiply the 8 times the 8. I would multiply the 5i times the 5i. I would multiply 8 and 5i, and again 8 and 5i. Now this is going to be minus 1. And so here we have 64 minus 25, which gives us 39. And 40 i's plus 40 more i's is 80 i's, and that would be this complex product, which is our answer B here. See if you can pause the video and try to do number 4, using that as a template. Let's see how you did. So we begin by FOILing. 9 times 2 is 18. Minus 4 times 9 is minus 36. I times I is I squared. Then we're going to have an 81i as well as a minus 8i. And recognizing that I squared is just minus 1, this becomes plus 36, giving us 54 for our real part. And for our imaginary part, 81 minus 8 is 73. So this is 73i, which we can find here. Questions 5 and 6 ask for the quotient of two complex numbers. Our strategy for dealing with complex quotients is to multiply by the conjugate of the denominator on the top and bottom. We're always allowed to multiply by 1, and so as long as we multiply by the same thing on the top and bottom of a fraction, we're fine. Multiplying a number by its conjugate has a nice property in that it turns it into a real number. We would wind up with c squared. We would wind up with minus d squared I squared, which is plus d squared. And the positive CDI has a minus CDI to cancel with it, and so there's no actual imaginary part down here. Now upstairs, we're going to get another complex number, but because this c squared plus d squared is a single real number, we're just going to get one number down here once we evaluate this, we can split up the fraction and really write it in complex standard form, a plus bi. So on top, just to remark, we're going to wind up with ac, we're going to wind up with minus dbi squared, which is plus bd. And then we're going to have a bc term and a minus ad term next to an I. Now, this fraction can be split up into two fractions like this over this common base, showing us that this is indeed in a plus bi form. This will be the complex number that we want. Now, I don't recommend memorizing this formula, but I do recommend knowing this, that the way you deal with a complex quotient is to multiply by the conjugate, changing the sign of the imaginary part on the top and bottom, and that will do it. Let's see how that works. So for number 5, I would take this fraction and I would multiply it top and bottom by the conjugate of the denominator. So changing the sign of the imaginary part, we get a plus 7 here, and we're going to multiply by these things on the top and bottom. That is going to require foiling, but the denominator is just a number times its conjugate, and so that's actually going to be pretty easy to get. That's 4 times 4 is 16. Minus 7 is minus 49, but I squared changes that to a plus 49, and our other two inner and outer terms, they cancel here. On the top, we're going to have 6 times 4. We're going to have 2i times 7i, which will of course turn into a minus 14. We're going to need 6 times 7i, which is plus 42i. And we're going to need 2i times 4, which is going to be 8i. This denominator is 65. 24 minus 14 is 10. And 42 plus 8 is 50. So that gives us 50i. Now we can split up these two fractions and reduce them. 10 over 65 reduces to 2/13, and 50 over 65 reduces to 10/13. So that gives us the following complex number as our quotient, which we see is right here. That's a good sign. So now pause the video and see if you can't get this one on your own. And let's see how you did. So let's take this guy and multiply on the top and bottom by the conjugate of the bottom. That's 5 minus 3i here and here. Foiling our denominator, we're going to get 25 plus 9 with our other two terms canceling, and our positive coming from the I squared, changing the sign. Then we're going to have 8 times 5, which is 40. We're going to have minus 6 times minus 3, which is positive 18. But we also have an I squared to watch out for there. Then we're going to have a minus 24i from the 8 times 3, and a minus 30i from the 5 times 6. For my denominator, 25 plus 9 is 34, and 40 minus 18 is going to give us 22. And minus 24 minus another 30 is minus 54, so we have minus 54i here. And splitting this apart and reducing, we get the following, which gives us b. Problem number 7 asks us to solve this equation, and we can see that it's actually a true rational equation. There is a variable in the denominator here, so we need to make sure that x equals 0 is not an answer to this equation, because x would be forbidden to have the value 0. We couldn't put 0 in any denominator. But with that caveat in mind, we can still use the idea of multiplying by the denominators to clear fractions. Let's see how that would work. So once I note that something is a rational equation, we have an equal sign and we have denominators, I would like to get rid of those fractions so that I could look at this just like a either linear or perhaps polynomial equation. How do we do that? We multiply by the denominators on each side. We're always allowed to do the same thing on both sides, and as long as x isn't 0, this would cancel this x and give us a nicer equation to work with. So our denominators are 5 and 6x. So I'm going to want to multiply by 5 on both sides, and I'm going to want to multiply by 6x on both sides. This one technically has a 1 for a denominator. We don't need to multiply by 1. It doesn't really do anything. On this side, there's only one term, and so we would just get a product in the denominator, which I could cancel to 1 directly. So on the right-hand side, I'm going to wind up with 2 times 6x. On the left-hand side, things are slightly more complicated because there are two terms and we are multiplying. So we need to distribute to both terms. That's going to give me 30x when we multiply by 1 here. And on this side, well, I'll have 6x over 6x. In this part here, the 6x over 6x is going to cancel. And we're just going to wind up with a minus 9. So that gives us minus 9, but then there's also this 5 hanging out. So we'll have to take that into account. So notice that we are multiplying both terms by 6x times 5. Here we have no cancellation at all, so we just get the full 6 times 5x. And here the 6x canceled, so we just have a 5 times 9 attached to this minus sign here. Let's clean that line up a little bit, and then I would proceed to solve it in the usual way. We want to group our x's together, so let's bring that 30x over to meet them. And that would give me minus 45 is equal to minus 18x. That negative 18 is multiplying my x here, so I would just divide to get rid of it. A negative divided by a negative is a positive, and we could reduce 45 over 18 because both 45 and 18 are divisible by 9, which gives us 5 halves as our reduced value, which would be answer D here. Question number 8 is another complex quotient problem, so you should definitely be able to get this one now. Think about what you need to do to start, multiplying on the top and bottom by the conjugate. All right, let's see how it went. Conjugate of the bottom is 5 minus 3i. If I FOIL on the bottom, I'm going to get 25 plus 9. And then at top, I'm going to get 25 minus 7 times minus 3 is positive 21, but they're I squared, so it's minus 21. And then for our I term, we're going to wind up with minus 35 and a minus 15. Keep in mind, I'm just FOILing here, but now if I group like terms and pull my I out to the front, we'll have the following, which we can reduce to 2 over 17 minus 25 over 17i, which is indeed answer C. Question number 9 asks us to solve a certain equation, which is set up as a square equal to a negative number. To solve something like this, we need to keep in mind two facts. One is the square root property, which tells us that we need both a plus and minus square root in order to fully solve this x squared type equation. And also, we need to know that the square root of negative 1 is I, since I squared is equal to negative 1. Using the first property, we can rewrite this as plus and minus the square root of negative 40, which is in turn the square root of 4 times 10 times minus 1. The reason I've written it this way is because we're going to want to reduce this radical, and we're going to want to pull the negative sign out as an I. Because there's this negative 1 here, we're just going to write this as an I out front. If we have the square root of the product of two things, that's the product of their square roots. And so I could look at the square root of 4 times the square root of 10, but the square root of 4 is 2. So just writing down the only thing left unsimplified, which is the square root of 10, we are done. You might have also learned to do this by breaking down 40 into its prime factors and then looking for pairs, because we're looking at a square root. There's a pair of 2's, so that comes out as a single 2. And there's only singles left inside, so no other pairs come out, and we still just get a 10 inside here. The answer given has chosen to pull the I up between the two. Multiplication is commutative and can be done in any order, and so that's just fine. The next is a similar one because we're asked to solve using the square root property. And this is a good way to go about it because here the only x's that we see are inside this parentheses, which is itself being squared. That means I really can start to chip away down towards my x by applying a square root to both sides. We use the square root property to write 7x minus 6 is equal to plus and minus the square root of 6. The square root of 6 doesn't reduce, so it's just going to come along for the ride looking just like that. However, to solve for x, we just need to add 6 and divide by 7 on both sides. Distributing this division by 7 gives us 6 over 7 plus and minus radical 6 over 7. I see here they haven't bothered to distribute. No worries, that's also an equivalent form of the answer. Numbers 11 and 12 ask us to solve the equation using the zero factor property, also called the zero product property. let's see how that would go. To solve, we need to first factor this polynomial. It has a leading term, which is not 1. So I would counsel the AC method in whatever form. That is to say, we're going to want to multiply 7 by 3 and look at its factors to find the middle term. However, in setting up my work, I prefer the following methodology. I will put a 7x in both of these positions and a 1 over 7 up front for balance, which ensures my leading term is still 7x squared. We know our signs. We'll have a plus, and then a plus times a minus will get me this minus. The benefit of doing this is now there's only 2 blanks left to fill, and it justifies why we multiplied a and c by each other. We put an extra 7 in here, so I'm not looking at factors of 3, I'm looking at factors of 3 times that extra 7. Now, what are we looking for? We're looking for a difference, because these signs are different, of 4 in factors of 21. We have 21 and 1, we have 7 and 3. Hey, there it is. So this, if you drop this sign straight down, you can always put your larger number there. And now all that's left to do is reduce. There's a common factor of 7 that could be pulled out of this, and that gives us x plus 1 times 7x minus 3. Where did the 1/7 go? Well, it times by 7 and turned into a 1. Now that we've written it in a factored form, we can set each factor equal to 0 to find our solutions. The zero product property, or the zero factor property, tells us that if a times b is equal to 0, this happens if and only if a is equal to 0 or b is equal to 0. So it gives us a way of writing equations that have been factored once they're set equal to 0 as 2 smaller, simpler equations, which is exactly what we're doing over here. If x plus 1 is equal to 0, x is minus 1. If 7x minus 3 is equal to 0, we add 3 and divide by 7 to get 3/7, which is answer A. So pause the video and try problem 12, which goes similarly, but with an even simpler factorization. Okay, let's see how you did. Number 12 is a monic polynomial, so we really don't have to worry about multiplying a by c. We don't have to worry about what factors are going to go in front here. We can just take this to be x and x if it factors over the integers at all. Dropping this sign straight down, a plus times a plus will give me this plus. And now we're looking for factors of 32, which, same sign, sum up to be 12. That's going to be 8 and 4, giving us solutions at minus 8 and minus 4, which is answer C. Questions 13, 14, and 15 ask us to use the quadratic formula to solve each of these quadratic equations. Let's recall that the quadratic equation tells us if we have the following general quadratic polynomial set equal to 0, we actually know the values that x can take on. It's going to be something of this form, where we have negative b plus and minus the square root of b squared minus 4ac all over 2a. Special emphasis should be placed on the b squared minus 4ac part, as that's going to tell us the kind of answer we're going to get, either 1 or 2 real numbers or a complex number if this is negative. So to use the quadratic equation to address problem number 13, we need to first set everything equal to 0 and then identify our a, b, and c. Here a is equal to 3, b is equal to 12, and c is equal to 2. And so we plug in a, b, and c into the positions above to get minus 12 plus and minus the square root of 12 squared minus 4 times 3 times 2 over 2 times 3. Let's evaluate to simplify that expression. And continuing to simplify this discriminant, we get the following. We can also simplify the square root of 120. We can pull out a pair of 2's, and what remains is 3 times 2 times 5. That is to say, the square root is also the square root of 4 times 30, which is 2 radical 30. And we can break this apart over the 6 in the denominator and simplify accordingly to get the following answer. Looking through our prospective answers, we can see that they really didn't buy into the whole distribute the denominator thing. So let's simplify a different way. From this line right here, we could pull a 2 out of every term from the top and bottom and cancel. That is to say, 2 could be taken out of 12 and 2, giving me minus 6 plus and minus radical 30. That's my numerator there. And on the denominator, we could write 6 as 3 times 2. Of course, the 2's then cancel, and we wind up with minus 6 plus and minus radical 30 over 3, which is indeed answer C. Questions 14 and 15 are similar. Pause the video at this time and see if you can get these for yourself. Okay, let's see how you did. Problem 14 is a quadratic equation, but it's not quite in the right form yet. We want to set it equal to 0. I like to leave my leading term positive, so I'm actually going to move these terms from right to left by adding them to both sides. This gives me 3x squared plus 10x plus 5 is equal to 0. Now we can see clearly what's A, what's B, and what's C. Plugging these into the quadratic equation, we get the following, which we can simplify by evaluating. Reducing this radical and factoring out and canceling a 2, we get the following answer, which corresponds to D. For number 15, we want to repeat this process. It's set equal to 0, so we identify our A as 1, our B as minus 14, and our C as 65. Plugging these into the quadratic formula, we get positive 14 plus and minus the square root of negative 14 squared minus 4 times 1 times 65 over 2 times 1. You are permitted a calculator, so don't feel too abashed about carrying out some trivial calculations on one. This radical will have the argument negative 64. That's great because 64 is actually a square. It's 8 squared. And so the negative sign here just means that there's going to be an I out front. So the square root of 64 is 8. So negative 64 square root is 8i. And this is all divided by 2. Now we really should divide that 2 in against both terms here, giving us 7 plus and minus 4i. Remember, that's two numbers, one for the plus and one for the minus. This, of course, corresponds to answer C. This next cluster of problems asks us to solve equations which have a square root involved. Note for problems 16 to 18 and any questions that involve a square root, we're going to want to check the answers that we get. That's because when we square both sides of an equation, we can introduce new solutions to the equation which weren't actually solutions to the original equation. For number 16, we're going to proceed to get rid of this square root by squaring both sides. If I do that, I wind up with x plus 3 on the left and x minus 3 squared on the right. Let's expand this. It's a perfect square trinomial, so that's x squared minus 6x plus 9 is equal to x plus 3. And now let's group like terms. Minusing my x to the other side and minusing my 3, we wind up with a minus 7x and a minus 6. This can be factored as x minus 6, x minus 1. And so we have solutions at x equals positive 6 and x equals positive 1. But we now have to check that these solutions that we got by squaring both sides both work. If I plug in 6, I get the square root of 6 plus 3. And we want to know, is that really truly equal to 6 minus 3? But we can see that it is because this is the square root of 9, and 6 minus 3 is just 3. So this is fine. So 6 is a solution, but what about 1? Okay, well, 1 plus 3, is that equal to, question mark, 1 minus 3? And what we see here is that it is not. We have a square root of 4, and this is not actually equal to negative 2. We're taking the principal root on the left-hand side. This is positive 2, but we got a minus 2 over on this side. So what this means is that 1 was not a valid solution for the problem. So we get rid of it, and we only report our 6 as a solution. Looking over here, that corresponds to entry number B, okay? Problems number 17 and 18 are similar, so pause the video and try them yourself. Let's see how you did. For 17, a key issue is going to be that we haven't quite isolated the square root yet. There's this mixture of square roots, but also regular x's on the left-hand side. So what we're going to want to do is first move that x to the right-hand side. Now the square root is the only thing that appears on this side, and so we can cancel it by squaring. Squaring both sides and expanding, we get the following polynomial equation. Now we can proceed the usual way. Let's group like terms. Taking 2x away from 12x, we get 10x. Taking 15 away from 36, we get 21. This factors as x plus 7 times x plus 3. And so my solutions, or at least my prospective solutions, are at minus 7 and minus 3. But as we saw, we need to check these answers against the original equation. We can either check them here, that's fine, or we can check them here at this second line, that's also fine. We need to do it before we square both sides though. So let's plug it into here. The question is the square root of 2 times negative 7 plus 15 equal to, in fact, negative 7 plus 6? Well, on the right-hand side, that's easy to see as minus 1. On the left-hand side, we get the square root of negative 14 plus 15, which is the square root of positive 1. Now, those two are not the same. The square root of positive 1 is positive 1, and this is a negative 1 over here. So we've ruled out a possible answer. Now, what about minus 3? The square root of 2 times minus 3 plus 15. Is that equal to negative 3 plus 6? And here we can see we're in luck. This is going to give us a positive 3 on this side. And over on the other side, we're going to wind up with negative 6 plus 15. That's positive 9. So yes, we do in fact get a correspondence here. And minus 3 will be one of our answers. So the answer corresponding to just a minus 3 is what we're going to want for 17. For 18, it's already isolated, our square root. So we're going to want to square both sides to get rid of that square root. So moving everything over to the left-hand side, we change signs as needed. And now we're going to factor. So we have an x and an x, a minus and a minus times a plus will give me a minus here. And now we're looking at factors of 12 with a difference of 4. That's going to be 6 and 2, biggest factor first. So this is going to give me solutions at positive 6 and minus 2. And we're going to want to check those in the original equation. If I take 6, is that in fact equal to the square root of 4 times 6 plus 12? Well, yes, it totally is, because 4 times 6 is 24, plus 12 is 36, and 36's square root is indeed 6. But what about minus 2? Is minus 2 what I'm going to get when I plug in minus 2 into this equation? And the answer is no. This is going to give us the square root of 4, positive 4, but that's equal to positive 2, not negative 2. So this one's not going to work when we plug it in to our original equation, and that rules it out as a solution. So only 6 will be an answer here for 18. Questions 19, 20, and 21 are asking us about solving inequalities. So let's see how we can approach those. What we want to remember is that equalities work very similarly to inequalities. The main difference between them is that if I have to multiply or divide by a negative number, then I need to also flip the direction of this inequality. This has to do with respecting the usual symmetry of inequalities. A is less than B if and only if B is greater than A. And also, if I were to minus A and B from both sides here, we would wind up with minus B less than or equal to minus A. Notice I didn't need to flip because I wasn't multiplying or dividing here. I am subtracting. That does not require us to switch the direction. But if I were to divide by a negative 1, as I'm going to do here, then they would have to be shifted. But notice that really I could also just sort of change the direction of this inequality. Negative A is greater than or equal to negative B. And comparing these two, we can also see the source of this rule here. It comes from needing this symmetry to hold and from being able to do both things on the same side with addition and subtraction. Those two together require us to flip inequalities when we multiply or divide by a negative. To distill this down into a simple rule, if you multiply or divide by a negative, you flip the inequality. Notice that doesn't matter if this C were negative, doesn't matter at all. What matters is that we are dividing on both sides here by negative 1. Let's see if we can see this in practice. Now, one thing we can do is arrange it so that we're not dividing by a negative at all. For example, if I add 7x to both sides here, I'll just wind up with a single positive coefficient at x on the left-hand side. Likewise, minusing 12 and minusing 12 here, I'll wind up with x is greater than 5, and that just settles it. Now, if you had done this a different way, if you had, for example, added 6x to both sides, then we would wind up with a minus x here. And likewise, subtracting 17, I'd wind up with a minus 5 here. Now, we could proceed here by getting rid of this negative sign by dividing by negative 1 or multiplying by negative 1 on both sides. And that is going to wind up turning these signs to positive. But it's also going to require us to flip the direction of this inequality. Because notice, we want these two answers to have to be equal to each other. So this is just more justification for why we need that rule. How do you graph something like this? What is its interval notation? Well, we're talking about all the values strictly greater than 5. So here is a graph of that. And we could mark that with interval notation, starting from 5 and going up to infinity. So that would be this answer C here. For number 20, we're going to proceed similarly. I can move my 12x from left to right, and in doing so, I make sure that I have a positive 1 for my coefficient. If I move my x's left to right, I'm going to want to move my numbers from right to left. So let's add 3 to both sides to do that. And we wind up with a 10. Now, I haven't done any division or multiplication by a negative, so this is going to be my final answer. We have 10 is greater than or equal to x, or x is less than or equal to 10, however you want to say it. Our critical value is 10. We are going to begin graphing on 10. We can use either a bracket or a filled-in circle. And we're going to want to shade all of the things where 10 is greater than x or where x is less than 10. That's going to be to the left here. So our bracket would face that way. We could put this in interval notation by starting at negative infinity, going up to 10, and including it. We always want to include it when we are dealing with inclusive inequalities that have equal signs to them. Scanning my answers, that's this one here. For 21, we have a nice opportunity to clear denominators, so let's do it. Here, we don't need to multiply by 15 and 12 and 60, although you could, and it would work out and simplify just fine. But to get rid of these fractions, a more streamlined approach than multiplying by every denominator is to multiply by the least common multiple of the denominators. You see, 15 goes into 60, and so does 12. So if I just multiply by 60, I'm going to kill every denominator. I need to do that on both sides. Notice that 12 goes into 60 5 times, and so we wind up with 5 times x minus 4. This is greater than or equal to, distributing my 60 to both terms, we're going to wind up 15 goes into 64 times, so 4 times x minus 3, and 60 goes into 60 once, so this is still plus 1. Let's distribute and combine like terms. Now let's combine like terms around the inequality. So I'll subtract 4x from both sides, and we wind up with a single x over here. Then I'm going to want to move my 20 to the other side. That's going to give me a 9. So we have that x is greater than or equal to 9. So we make a mark at 9. We shade it in, and we shade all the values greater than that, which gets me a graph that looks like this, or an interval that looks like this, with a bracket up to, from 9 up to infinity, which is answer C. The next questions are asking us to evaluate a little bit of function notation. What we need to know is that this place held by the 3 here is the place held by the x in the general rules of f of x. That means we're going to replace x with a 3 in order to find what f of 3 is. So we go through our rules for f of x, and we replace our x's with 3's. We need to follow the rules of PEMDAS, and so we do our squares first, then multiplication and division, and finally addition and subtraction, which gives us our answer. For 23, we have something just slightly trickier. We are still doing a substitution. Instead of x, they want the expression k minus 1 plugged in. So we just take our rules for f of x, which say take the thing and square it, times it by 4, add that to 3 times the thing, and then add 4 to that. And we just replace that thing x with a k minus 1. So we want this to say 4 times k minus 1 squared, plus 3 times k minus 1 plus 4. And now we just have to work out this algebra. So if I square this thing, doing that part first, we're going to get k squared minus 2k plus 1. That's our perfect square trinomial formula there. Or you could write this next to each other, k minus 1 times k minus 1, and then FOIL it out. Let's distribute and combine our like terms. There's only just the 4k squared for a k squared term. I've got, oh, why did I make this an x? That's silly. These are k's. And then combining our k's, we have a 3k and a minus 8k, that's minus 5k. And we've got 4 plus 4 is 8, minus 3 is plus 5. So that's our constant term. Matching this to our answers, we can see that's answer D. 24 is asking us to find f of 16. They've sort of laid out here that y is what we mean by f of x, that f of x gives us a y value. So this is essentially saying, what is my y value when x is equal to 16? So where is x equal to 16? Well, this is 20. That's 1, 2, 3, 4, 5 tick marks. So each one of these tick marks must be worth 4 units. And so going over 1, 2, 3, 4 units, that's going to give me my 16 for my x value. And then where is the y value of the graph plotted? Well, it's right here. And going over, this apparently is at this particular tick mark. So that's 5, that's going to be at 8, right? These are also still 4 units apiece, 5 units, 5 tick marks, bringing us up to 20. So this y value is in fact an 8. And that's going to settle it. Moving on. The next few questions ask us about this graph. They have recorded hourly temperatures across these particular times. They ask for where is it at its highest, which means finding this peak. At what time is that peak acquired? Well, we look down here and we see that that's at 1 p.m. What temperature was recorded at 5 p.m.? Well, here's 5 p.m. So I could look up from there and find its value, and then look over from that to read it off the y values. That's 76 degrees Fahrenheit. Likewise, where they say, when was it higher than 77? Well, here's 77. It's right between 76 and 78. And where is it higher than that? Not equal to it, but higher than that. Well, it's going to be just after this value. So let's maybe even put an open circle there to mark that. And then all along this interval here and all along this interval here, although maybe not including this endpoint, it is in fact higher than 77. So what are those values? Well, that's from 12 up to 3, and they give us an answer for that from 12 until 3. That's answer C. And that's all there is to that one. 28 and 29 are asking us about domain and ranges of a graph. If a graph consists of a collection of points of the form x comma y, then the domain of that relation will be all the x values which are used in that collection, and the range of that relation will be all the y values used in that collection that represents the graph. Another thing that's necessary in order to understand how to process what's going on in 28 is we need to know something about parabolas. We need to identify this shape here as a parabola. It has this characteristic kind of U shape. It seems to be steepening, or maybe in this case, getting shallower and shallower, less and less steep because it's pointed to the side. But we need to recognize this as a parabola. That is pretty important. Essentially, it looks like the graph of x squared. And while there's a bunch of really great lore that you should probably be aware of at this point about parabolas, the main thing we need to be aware of here is that parabolas widen forever. They get wider and wider. Even though they're getting steeper, they still get wider forever. They never get to a widest point. As such, this parabola over here is going to expand in the vertical direction forever. It's going to keep getting wider and wider as it goes, even as it's getting shallower and shallower. And because of that, our range is going to be from negative infinity to positive infinity. Now, what about our domain? Well, not all x values are used in this graph. If I look over here at these negatives, there is no graph above or below negative x values over here. The only time that I start to see graph is when I get far enough over, when I get to this point here. Then I can see some graph. Then we actually hit this vertex at 3, looks like -3. And then ever after that, these x values have companion points on the graph. Now we have some graph underneath that x value. And so these x values will be in the domain. So what is my domain? Well, it starts at 3, and in fact, it's going to include that 3. Vertexes will always be included in the parabola's domain. And so this is going to be our final answer. Likewise, in this one, when we do our domain, we want to take a look at its x values that are used. No negative x values appear, but 0 appears, and also all of these values here. Again, we're going to have to recognize this is part of a parabola. Actually, it's sort of more like the branch of a square root function, but a square root function is really just the parabola on its side. So it widens forever as well. So when it comes to our range, this might be the lowest value for y, but it's going to continue to go up and up and up as this thing widens forever. So what are my x and y values? What are my domain and range? The domain will be from 0 to infinity, and the range will be from -3 to infinity. And so A is our answer. Question 30 asks, where is the function increasing, decreasing, or constant? A function is decreasing if it goes down as we travel to the right. Notice that as we increase our x values, this function's y values go down along this interval. From here to here, they are in fact not going up or down. They are staying constant as we increase our x values. And here, as we increase our x values, we are increasing. So let's decode that into the answer. This appears to be the point -3. We never want to use brackets as part of our values here, and that is principally because at these corners, it is neither increasing nor decreasing nor constant. It is changing its characteristics. And so that and that alone tells us enough to rule out A, B, and C and to select D preferentially. But let's make sure everything lines up, shall we? So this is decreasing up to -3, which is here. And yep, that's true. It's constant from -3 to +3. Yep, that's looking true as well. And then from +3 onward, it is in fact increasing. So this looks to be our correct answer is D. 31 to 33 ask us whether a function is even, odd, or neither. Even functions are symmetric with the y-axis. Specifically, they have reflective symmetry around the y-axis. This means that if I attain some particular value, x, let's call it f of x, that's precisely the same value I'm going to get on the other side if I look down at minus x. So in other words, we have that f of minus x is precisely what I get when I plug in x itself. Changing the sign doesn't matter. Notice that a good example of things which have even symmetry are things like even powers. So for example, if I took f of x to be equal to x squared, well, f of -x is also x squared. So we wind up with the same value for f of -x as we do for f of x. On the other hand, for odd functions, we are symmetric in a different way. We are symmetric about the origin, specifically rotation by 180 degrees around the origin. In this picture, if this x has a value f of x, then -x has to have exactly the negative value of that in order to have this kind of rotational symmetry, which gives us another rule that we can use to check if something is odd. Plugging in -x should give me the negative value of what I get when I plug in x. And an example of this is going to be odd polynomials, that is to say, polynomials of odd degree only. For example, if I have x cubed, if I plugged in -x into that, I would have -x times itself 3 times. And that odd number of -1s times themselves would give me a negative times x cubed. So this is in fact negative f of x again. Now f of x, but just with a negative sign pulled out. So every time we see an odd exponent, that's going to pull a negative sign out when I plug in -x into that. And if something doesn't have symmetry, then it is in fact going to be neither odd nor even. If there are zeros on one side that don't correspond to zeros on the other side, either in multiplicity or location, then that's enough to rule out that something is odd or even. And also, we just need to note that plugging in -x would simply not be equal to either f of x or -f of x. If it's neither of those, then it's neither odd nor even. Finally, as an example of that, any polynomial that has a mixture of powers, odd and even powers, are going to have an issue where I go to plug in -x. Some of them are going to stay as they were. The even powers will get rid of that -x. But the odd powers are going to switch signs. And so this f of -x really isn't the same thing at all as f of x. They're quite different, actually. They have different roots, and they have this different distribution of signs. So if we see a mixture of powers, odd, like this one here, and even, then we know it's going to be neither. Let's address that on the problems 31, 32, 33. If we take the rules for 31's f of x and we plug in -x, let's see what we get. Notice that the only powers we're taking here are even ones, and so that's going to kill these negative signs. And this is in turn exactly f of x again, and so that tells us that this one is even. On the other hand, for 32, if I plug in -x into the rules for f of x, all of these odd powers are going to keep those negative signs, which changes the sign here and here. Now notice if I factored out a -1, then we could see this is exactly negative f of x. And this tells us that the thing we are looking at is odd. We could have also just looked at these odd exponents and determined that. So 32 is odd. And for 33, well, 33 has a mixture of parities. They have 3 and 2, that's odd and even. So we know this is not going to be either odd or even as a function, but let's just see when we plug in negative x what happens. We have 3 times negative x to the third power minus 2 times negative x to the second power minus 4. One of these is going to reverse the sign. The other is going to keep the same sign. And minus 4, this other even term, keeps its sign. So notice that there isn't a way I can pull out negative 1 and just get f of x again. Neither is this f of x itself. So this is not equal to f of x. It's not equal to minus f of x. And so this is neither. Once we notice that there's this mixture of odd and even exponents, we can also rule that any polynomial of that kind is neither even nor odd. So that is C for this one. The next few questions are questions about lines. The first is asking for a calculation of slope. To calculate this, we're going to need how to calculate slope in terms of its x and y components. Slope is a ratio describing the change in our y component versus the change in our x component. And if I am given x1, y1 as a single point and x2, y2 as some other point, then the change in y can be calculated from the difference of those two y values. And the change in x can be calculated by the corresponding change, the corresponding difference in the two x values. So we really just want to plug things in to this formula. Now, when you do this, keep in mind you need to take the difference in the numerator, the difference in the denominator, and divide them. So I would, when you plug this into a calculator, if you do so, encourage you to put parentheses around the top and bottom, but that's just a good tip when you're dealing with quotients anyway. So 34 asks us to calculate the slope of a line through these 2 points. And really what we want to make sure we do is just label either one as our x1, y1 and the other one as our x2, y2. It really doesn't matter which point they give you first. There is a symmetry in the equation for slope that makes that the case. Your slope will then be given by negative 5 minus 2 divided by negative 9 minus 1. And we just want to be diligent about our sign rules here. This is minus 5 plus 2 over minus 9 plus 1. In other words, minus 3 over minus 8, which gives us positive 3/8. We can approach 35 the same way. We just want to be careful. The reason we're going to want to be careful is our two x values here match. If the two x values match, that means we're dealing with a vertical line, as long as they give us two different y values. And vertical lines have an undefined slope. Let's see why in the formula for slope. So formula for slope is the ratio of the change in y, or y2 minus y1, 3 in this case minus 6, divided by x2 minus x1. But this gives us a value divided by 0, which is undefined. If the situation had been reversed and it had been a horizontal line or a y value that had repeated, we would have 0 in the numerator, which is not a problem and would just give us a 0 slope. But as it stands, this one gives us a undefined slope. The next 3 problems ask us for the equation in slope-intercept form for a line having certain properties, either going through 2 points or having a certain point that it goes through and a certain slope. For problems 36 to 41, we're going to want to keep in mind a special form of a line called point-slope form. This is a form of a line that goes through the point x1, y1 and has a slope of m. Let's see how we would use that to settle these problems. So for 36, for example, we want to identify this as our x1, y1, and tuck those in the right place. This will give us y minus 9 is equal to negative 5 times x minus 7, which will be plus 7. To get this into slope-intercept form, or y equals mx plus b form, we want to first distribute that minus 5 against both terms inside, and then we want to bring this 9 over by adding, and that's going to give us y equals minus 5x minus 26, which we can find here. For 37, we're given that the line goes through these 2 points, so let's call these our x1, y1 and our x2, y2. We first need to calculate the slope, which we do the usual way. y2 minus y1 over x2 minus x1, which is going to be minus 4 minus 9 over 0 minus 3, which is going to give us negative 13 over negative 3 or positive 13 over 3. And we could plug this into point slope form, but we should probably notice that they've given us the y-intercept. When we write things in y equals mx plus b form, we're trying to find the slope, m, and the y-intercept, b. Well, the y-intercept b is the value of y when x is equal to 0, and they've just given me that as minus 4. So rather than plug things into the point-slope form equation, let's just plug things straight into slope-intercept form. That's going to give me 13 over 3x minus 4 is equal to y, which is this one right here. Question 38 asks us for something very similar, but here they've told us that our line goes through these two generic points instead of through a particular y-intercept. So we just first want to find the slope by identifying which one of these will be our x1, y1, and our x2, y2. Plugging these into our slope equation, we get 9 over positive 5. And then we could use the point slope form equation to get us the rest of the way. We take y minus y1, and then take the slope 9/5 and multiply that by x minus x1, which would give us x plus 7. So this minus a minus is going to make this a positive 4 over here. And so to get rid of it, I'm going to want to subtract 4, but let's distribute our 9/5 first. So minusing 4 from this side, I'm honestly going to minus 20/5 from this side, which is the same thing as minusing 4. Convince yourself that that is the case. But that's going to give us 43/5. So we have y equal to 9/5 x plus 43/5, which is right here. Continuing on. Here we have 3 more problems that deal with giving a prescribed line based on certain facts. The first one is just like we had before, but hey, let's notice that they really have given us everything we need to get this in y equals mx plus b form right off the bat. This is a y-intercept after all, so actually this tells me b is equal to 5. And they've given me m, so if what they wanted was slope-intercept form, we know it already. It's 5 over 9x plus 5. But they actually want it in standard form. So let's take that to the side for a moment. So we were told these two things. We can get a y-intercept form this way. Standard form looks like this, where a, b, and c are integers, if possible, and where a is some positive value. So the way that we would go about doing this is to first get the x's and y's on the same side. I could do that by subtracting 5/9 x from both sides, which would give us the following. And now multiplying by minus 9 on both sides of this equation is going to get rid of this denominator and rewrite them as a whole value. In fact, the leading term will then be positive as well. So we're going to want to hit both sides with a minus 9, distribute, and canceling appropriately, this gives us 5x minus 9y is equal to negative 45, which we can find for number A. Notice how similar the rest of them were. We have to be very careful with our signs here. For questions 40 and 41, we're given things about parallelity and perpendicularity compared to certain lines, and then we're asked to find other lines in slope-intercept form. We have to remember there is a relationship between slopes and parallelity. The slope of a parallel line to a given line, which I will write using this symbol, which looks like an 11, but really it's parallel lines. Parallel lines have equal slope to one another. On the other hand, if what I really wanted was the perpendicular slope to a given line, which gets this funny symbol, meaning perpendicular or at a right angle to something, that's going to require us to take the slope of a given line and take its negative reciprocal, or 1 over the original slope, and then with a sign change. Let's see how that would pertain to the given problems. So 40 asks for a line parallel to this given line that goes through this other point. And the main idea here is we want to know what slope it has. Well, let's just solve for y. This gives us minus 6x plus 4. So we know that the original slope was equal to minus 6. And since we're looking at a line parallel, we know our new slope is going to have minus 6 as well. So let's write down in point slope form what it would mean to go through the point 3, 4. So these will be my x1, y1 in that equation. And we'll then have y minus 4 equal to negative 6 times x minus 3. There's our point slope form for it. And all we have to do now is solve for y in order to get it into slope-intercept form. So solving for y is going to mean distributing this minus 6 and adding 4 to both sides, to get y equals minus 6x plus 22. That's answer D. 41 is similar, but now they're asking for the perpendicular line. We still need to find out what the original slope is, and the easiest way to do that is to put it in slope-intercept form and look at the coefficient of x. And this gives us a slope of 5, and so the perpendicular slope will be the negative reciprocal of 5, or 1 over 5, times negative 1. So this is going to give us minus 1 over 5. We want to put that into the point slope form equation. Y minus 3 equals negative 1/5 times x minus 4. Solving for y means distributing the minus 1/5 x and adding 3 to both sides to move that. Collecting our like terms, we find negative 1/5 x plus 19 over 5, which is answer A. Be very careful about all the nearby answers. Question 42 asks us to graph a given function and state its domain and range. This function is a linear function, meaning its graph will be a line. It's in y equals mx plus b form already, where y is being played by f of x, m is being played by this minus 5 here, and our b is being played by this 2 here. So what's that all mean? Let's start at the point 0, 2. We know when x is 0, f of x, or y, will be positive 2. So we know it will be at such a point. And its slope is minus 5. That means that when we go over to the right by 1, we're going to go down by 5. That's the interpretation of minus 5 over 1 as being our slope. We recall that this top number gives us the rise and the bottom number gives us the run, although I like to think about this as being running to the right. And then this sign here tells me then that I'm going down. And we're going from this point right by 1 and down by 5. So from 0, 2, right by 1, down by 5, this brings us to another point, and these 2 points together give us a sketch of a graph. And we can use that to go and match this one. Notice that all of the domains and ranges all say negative infinity to positive infinity. And that's true for all lines, which are not vertical lines. And horizontal lines have a single point for their range, but the domain will still be negative infinity to infinity. All slanted lines, such as this, domain and range, both negative infinity to positive infinity. These lines go left and right forever, and they also go up and down forever. So that gives us B here. 43 gives us another graph. It is going to be a line. We can find its slope, but it's even easier to find 2 points just given intercepts on this one. But actually, it looks like both the x and y intercept are going to be 0. Notice that if I plug in 0 for x, then this term would become 0. And then we would also just get y is equal to 0. And so that means that our x and y intercept are both the same point. The intercepts are at the origin, and so this is both an x and y intercept. So we actually do need to get one more value for the slope. Let's see about what that would look like if I just take 3x minus 6y and I solve this for y by first minusing over the 3x and dividing off the minus 6. We find a slope of 1/2. So I need through the origin with a slope of 1/2. This again means we go to the right by 2 and we go up by 1. So from the origin here, I go over 2 up 1. There's my other point. Connecting these 2 points is going to give us a sketch of a line, which leads us to C as the closest matching answer. Moving on. 44 asks us to address this piecewise function. Recall that piecewise functions give us different rules for different intervals. This one tells us what to do if x is less than or equal to -1, and separately if it's greater than -1. So what about minus 4? Well, to do this, we have to decide which of these two intervals minus 4 falls into. Is minus 4 greater than -1, or is it less than or equal to -1? It is less than or equal to -1. And so what we want to do to evaluate f of minus 4 is to plug in minus 4 into the rules associated with being less than or equal to -1. That is to say, what is 2 times that? And this is going to give us minus 8, and that is answer A. Question 45 is looking for a graph. It says that it looks like this line, 2x plus 9, when x is less than or equal to 0, and it looks like this parabola, 2x squared minus 1, if x is greater than or equal to 0. I like to try to do a sketch of these and then match it. This graph of 2x plus 9, it would normally have a y-intercept of 9, which would be here. I'm going to leave that as an open circle, though, because this is strict inequality. Now, the slope is 2x. Normally, we go right and up by 2 in order to find those next points. But this is, again, bigger than 0. I have to constrain myself to be less than 0. So we can still get the slope of 2. We need to go back by 1, though, and down by 2, right? This still is increasing as we go to the right with a slope of 2. So connecting a few of those points just to show where we're going with this, right? That's our line good enough. What about this one? Well, this has been downshifted by 1, and x squared has been vertically scaled by 2. First of all, let's plot the point when x is equal to 0. That's going to be a value of -1. So let's put a filled in circle there because this is an or equal to. And then we're going to have a parabola. If I go up by 1, plugging in x is 1, I would get 2 minus 1 is 1. Or plugging in a 2 here, I would get 4 times 2 is 8, minus 1 is 7. And so this gives me enough points that I could plot a couple of values for my parabola. And this should give us enough to match the graph. Parabola on the left, line on the right, and the correct endpoints, open and closed respectively like this, we can see that B is going to be our graph. All right, let's keep going. 46 gives us the graph of a parabola and asks us to identify its equation. Now, what we should do is think of this as a transformation of some original parent parabola, which might have had a vertex at 0, 0, over to this new one. And where is it now? Well, we have an x value of 5 and a y value of 2. So this means it's been upshifted by 2. That corresponds to these transformations. And it has been right shifted by 5. That's going to actually correspond to this -5 composed with x squared. So this is going to be the graph that we are looking for here. And we can get that just by noticing that 5 and that 2 at the vertex point. I would encourage you to go back to some of those transformation videos and brush up on your function transformations as part of your review. Questions 47 to 51 are asking us a little bit about function algebra. F plus g of x is really just f of x plus g of x. Now, f of x was given by 9 minus 7x, and g of x is given by minus 2x squared plus 7 itself. Now we can just group like terms. We have minus 2x squared alone. We have minus 7x alone. But 9 and 7 are like, so we can combine those to get 16, which gives us answer C. Here we're asked to take a product of f and g. F times g of x is equal to f of x times g of x. So we're going to want to take 3x minus 4 and multiply that by 7x plus 3. But this is, of course, just foiling, from which we get 21x squared minus 28x plus 9x minus 12. But then if we group our like terms of the 28 and 9x, we get minus 19, which gives us D for our answer. Number 49 asks us to find g composed with f of 40, when f of x is x minus 4 over 6, and g of x is 4x plus 6. G composed with f is perhaps better written this way, so we can really see what's going on. We're going to need to be plugging in 40 first into f of x, and then whatever that is gets plugged into g of x. So for example, we might ask, what is g of 40 minus 4 over 6? Well, 36 divided by 6 is 6, so this is really just g of 6. And then g says, take 4 and multiply it by that, and add 6 to it, which is going to give us 30 right here. 50 is asking for a difference of two functions. F minus g of x is really just f of x minus g of x. And so to find f minus g of 5, we really just need to take f of 5 and subtract g of 5. Well, f of 5 minus 2 5 squared plus 5 minus 5 minus 6. Let's put some parentheses around these so we can remember what we're subtracting from whom. And this is going to give me minus 2 times 25 plus 5 minus 1. So this will be negative 50 plus 6. Or negative 44, which is C. Number 51 wants us to evaluate this function composition with f and g given. This is, of course, going to be equal to f with g plugged into that. So we want to take g's rules, which are 4x minus 1, and plug them into f's rules, which are 7 times that, so 7 times 4x minus 1 now, plus 14. Distributing by 7, I get 28x minus 7 plus 14 leaves me with 28x plus 7, which is right here. For 52 and 53, all we really need to know is the standard form equation for a circle, and then this is just plug and play. The equation for a circle of radius r with center hk in standard form is given as follows. X minus h squared plus y minus k squared is equal to r squared. So when we're given something like 52, we really just need to figure out what's our h, what's our k, and what's our r, and plug it into that equation respectively. We're going to have r squared, so we're going to be picking one of these with a 9 over here. And we really just have to make sure that our signs are straight. The equation calls for a minus sign, so it'll be x minus minus 6. That's the same as x plus 6. Likewise for the minus 4 here, our answer is D. Similarly, our h for this is going to be negative 8. Our k is negative 6. And that's going to put a 8, positive 8 next to our x, a positive 6 next to our y, and then the radius is the square root of 17. But the square of that is just 17. So here we have our equation in standard form as number C. These other problems ask us to graph a circle. The first thing we want to do is note our h and k. Here we have h equal to 4, k equal to 3. So we want to plot a point at 4, 3. That's right here. And then this r is going to be 4 because this is 16, or r squared. So then we want to go out a radius 4 from that point. I suggest going over by 4 and also up by 4 to plot some nice convenient points here. And then we can connect those points with the sketch of a circle, just to give us something we can match with a graph. Here we can see our closest match, and so our answer is going to be D as such. All right, moving on. To find the radius and center of the circle, we're really just going to want to put these into standard form. That's the quickest and best way to do this, so how do we do that? The answer is going to be completing the square. It's an excellent technique here used to factor out a square from our x and y terms and write that as a composition of x and y with some translation. So let's write these as our x terms first. We have an x squared, we have a 12x, and leave yourself a little blank. And then we're going to want a y squared minus 2y. And let's leave another blank and bring our 28 to the other side. From here, what I'm going to do is I'm going to add a special number that's going to allow me to factor this as a perfect square trinomial. That will be half of this linear coefficient, 12, squared. So half of the 12 is 6, squared is 36. So I'm going to add 36 to this equation here. And I'm also going to want to do it on the other side. Likewise, half of negative 2 is negative 1, squared is positive 1. So I'm going to want to add a positive 1 to both sides. Now, the reason that I've done this is because now this factors as a perfect square trinomial. In other words, we get x plus 6 squared and also y minus 1 squared. And that's going to be equal to 9. This lets me know that the center is at minus 6, 1, and that the radius is 3, which is answer D here. 56 is similar, so you should pause the video at this time and give it a shot yourself. All right, let's see how it went. So same setup as before. I want my x's pulled out front, leave a little space, and then put our y's. We bring our 32 over to the other side. What we want to do is take half of negative 8 and square it to give me 16, and add that here, and to the other side as well. Likewise, taking half of minus 10 and squaring it, we get 25, and I add that to the other side as well. 41 minus 32 is also 9. And now these perfect square trinomials will factor as such. X minus 4 squared plus y minus 5 squared. And so we have a center at 4, 5 and a radius of 3. This corresponds again to answer D. Let's keep going. Question 57 asks us to find an inverse to this function if it is 1-to-1. A 1-to-1 function is one that passes the horizontal line test. For every single y value, there's only one x value that will be given by that particular function. A function which doubles back on itself and gives two x values for a single y value would not be a 1-to-1 function. And it's the 1-to-1 functions which are going to have an inverse, which is itself a function. Now, we'll see that when we go to try to find an inverse. The procedure goes something like this. let's call f of x the output y, and inverses switch the role of output and input. If a function took this x and sent it to y, then the inverse would take the value y and send it back to x. So we can do that here by switching the x and y symbols. But now we're going to want to solve this thing for y. We do that with our inverse operations, and this is going to accumulate those inverse operations in a way that produces the inverse function. Now, if, say, for example, we had gotten to this step and it had been a 2, and so, or a 4, or another even power, then this would have a plus and minus in front, and that would be 2 values instead of just 1, and hence would not be a function. But as for odd roots, this will be a single value, and this will therefore be a function. And this function is our inverse of f, which we write this way. So we find this guy here as answer B, and we continue. Question 58 asks us for something similar. We write our function down, we give it the dependent variable named y, we switch. Everywhere I see an x, I put a y. Everywhere I see a y, I put an x, and then we solve for y. So bringing this 1 over, dividing by -5, we have our inverse function. Now, the form might be as such, or it might distribute that division by -5 against both terms and give us a -1/5 for our slope and a +1/5 for a y-intercept, and the inverse of this line was in fact this line. This should make sense in light of the geometric interpretation of what an inverse is. Interchanging x's and y's flip things over the line y equals x. Just imagine what switching x and y would do to the x and y axis, and we can see why that's the case. And this inverse that we have here is indeed going to be a reflection over that line, and that's here given as answer D. 59 gives us a square root. It's the squares we really have to watch out for, and other even powers. We really just want to make sure that it's one-to-one in the course of solving for the inverse function. So let's go look at that over here. So here we have 59, and we can see that really when they told us that x was greater than or equal to -9, that's true really just because of the domain of f of x, right? The square root or even root functions need to take in positive or at least non-negative arguments, or they become complex. So we usually limit our domain in this way. And if we do our process of setting y equal to f of x, then switching x and y, and then solving for y again, we get this parabola x squared minus 9. And that is our inverse up to a point. This branch of the parabola here is the inverse of this square root or sideways parabola here. And the idea is that if we had instead asked about this upright parabola in the first place, which if we included this left-hand side would not be a one-to-one function, well, then in order to give it a restricted domain such that the inverse of this green parabola was a function, namely this one, f of x, we would have had to have made sure that this thing was positive. That is to say, we would only want to look at this right-hand side of the parabola if this had been the one we were finding the inverse of. And we notice that that branch of the parabola is just the ones where x is greater than or equal to 0. So this green branch here and this yellow branch here are the inverses of each other, and not really the full parabola x squared minus 9. And they were kind enough to provide us that restriction here. Question 60, we're asked to find domain and range. We need to be able to eyeball a parabola in this class, but they did give us this equation, which definitely tells us this is a parabola. This is a parabola that has been downshifted by 5 and right shifted by 2. And so our vertex would have gone from the origin down to here. And the thing you have to know about this parabola is that, number one, it widens forever, and equivalently, any x value that you want could have been plugged into this function, and so the domain is -infinity to +infinity. That is to say, there are no restrictions on the x's that could be plugged in, so the domain is the whole real number line. On the other hand, the range, well, the lowest point on this graph, the lowest y value it attains is -5, and it doesn't get any lower than that. So we want to include -5, but we also want to exclude anything that's lower than -5. So we do that in this way. We say the range goes from -5 and including -5 up to infinity. And this is answer D. Question 61 and 62 are similar, but they're asking us to do that for these quadratic equations without looking at a graph, which is fine. We're still going to follow the same kind of thought process, and a quick sketch of a graph might even be really helpful. It doesn't necessarily have to be anything fancy. We just need to know that this is a parabola, because this is a quadratic polynomial. It opens up because our leading term would be a positive one, and that its vertex will therefore be its lowest point because it's opening up. Then what is that lowest point? Well, the vertex here is going to be something we've left shifted by 1 and up shifted by 6. So it's going to be at minus 1, 6. That means our lowest point is going to be 6. And our domain, as usual, is all real numbers, because any number we like could be plugged in here. There are no domain restrictions. Likewise, 62 asks for domain and range, but now they've given it to us in an expanded form. Well, we can look at the leading coefficient still and see that this parabola opens up, and so its vertex will be its lowest point. And we might also like the piece of lore that tells us that vertices of parabolas are at the value x equals negative b over 2a, where this is written ax squared plus bx plus c. So if we plug in these values, b is 10 and a is 1, we wind up with negative 5. And plugging back negative 5 into this function, we find a y value of minus 10. So this is going to be our lowest y value because the parabola is opening up. Our domain is still negative infinity to positive infinity, but our range now goes from negative 10 up to infinity, including negative 10. 63 asks us to determine whether or not this is a min or max and what that min or max is. It's a parabola opening down, and so that means its vertex is its highest point. So our quadratic function will have a maximum at its vertex, and that vertex is at x equals negative b over 2a. So we extract those values. B is negative 2 itself, and a is negative 1. And plugging them in, we find that this works out to be minus 1. Plugging in minus 1, we can find the y value of the vertex, and that tells us what this maximum value is. So we plug that into this function here and evaluate. That'll give us a minus 3 if we take care with our signs. And so this thing has a maximum value, a y value of minus 3. 64 gives us a function that they want us to maximize. And fortunately, this is a quadratic opening down. So that's easily done by finding the vertex. We note that b here is 1280 and a is negative 5. Plugging those into our equation for the x value of the vertex, we find 128. Finally, plugging 128 back into the revenue function, we get the value 81,920. 65 asks us to graph this function, and although it's a multiple choice question, it's nice to be able to just sketch that and then match this with one of the graphs. We could look at a parent function, y equals square root of x. You should know what that looks like at this point. And we could then shift it down by 2 and right by 6 to find the corresponding graph in yellow here of the equation in 65. And that's going to be something that looks like this. So then going and matching to our pictures here, we can see this one is the one which matches the sketch of our graph, and so we continue. Again, finding the match of this graph for 66 is going to be a matter of finding a parent function where we know what this is going to look like grossly. This is an absolute value function, and so it's going to look like a V shape with this hard 90-degree angle at the origin. But this has been right shifted by 7, because we have a minus 7 composed with the x, and up shifted by 2, because we have this additional plus 2 at the end of the equation. That moves us from the vertex over to 7, 2 for our, well, kind of vertex of this absolute value function here. And so now we can try to match to find this purple graph. That's going to be right here, and so we can continue. Questions 67 and 68 pertain to something called the leading coefficient test for polynomials. This is going to tell us the long-term or end behavior of the polynomial, and it depends really only on the leading term, that is to say the term with the highest exponent. We find that monomial, that is our leading term, and then we look at a and we look at n. We want to check a for its sign, positive or negative, and we want to check n for its parity, either being even or odd. And depending on if this is even or odd, positive or negative, we can match it to one of these 4 end behaviors. Let's take a look at what they are and try to come up with a slick way of memorizing it. I like to think about an example polynomial. Like, for example, this kind of looks like a parabola in the way that it rises on both sides. What it actually does in the middle, we don't know, because this might actually be some weird, complicated, wiggly polynomial in the middle. But at the edges, it's going to look like a square. And for positive parabolas, that goes up and up on the right and left, respectively. And for negatives, well, that goes down and down. Now, on the other hand, for odds, it's kind of split. I like to think about the cubic function here, or maybe just even the line y equals x. It rises on the right and falls on the left. What it does in the middle, we don't know, but at the ends, it's going to go up on the right and down on the left. Now, negating it would change that behavior in the same way that it did over here. It would flip the directions of the arrows, and that would make it rise on the left and fall on the right instead. So to answer these two, we really just have to look at the leading coefficient and say, is it negative? And what is the parity of the exponent? It is negative. This is a negative one. And the parity is odd. That tells us that it's going to rise on the left and fall on the right. This one here is positive, and the parity of its exponent is even. So it's going to rise on both sides, and that's answer A as well. Question 69 asks us to break down the zeros and the multiplicities of those zeros for this polynomial. This is easy to do with a polynomial when it is in its factored form. We can factor every polynomial over the complex numbers anyway, like this, where these r's are the zeros of the polynomial, also called its roots, and the exponent of that term, or the number of times the term x minus r is repeated, is the multiplicity of that root. So you can see for 69, it's already in its factored form. It's written as a product. This 2 and this 3 are exponents here. And this tells us that we have a 0 at minus 8, and its multiplicity is 2. Here we have a 0 at positive 8, and its multiplicity is 3. One of the nice things about having a polynomial laid out like this is by noting that the leading term would be 3x to the 5th power, we know that this has the following long-term behavior of falling on the left and rising on the right. We know it has a 0 at negative 8 with multiplicity 2. Even multiplicity zeros will sort of bounce off their zeros like this. And at positive 8, we know we have another 0 where it has multiplicity 3, which crosses and gives us the following sketch of this polynomial here. So you can get a pretty good sketch of polynomials just by knowing a bit about the multiplicities of their zeros and their n-term behavior. Of course, to get a better one, we'd need more points, more information about what goes on here, but that's one of the nice things about this setup, is that it gives us a quick sketch of the graph. Question 70 is quite similar, but now the leading term, instead of being a 3, is 2x. So there's no way to make a 3 into a 0, but you can make a 2x into a 0 just by making x be 0. And that'll be true if we have any monomial involving x to the power of 1 or greater up front. You'll always have a 0 at 0. Now, each of these terms, the 2x, the x minus 6, and the x plus 9, all have first powers above them because we don't see any exponents. They are first powers. And that means their multiplicity is 1. So each multiplicity will be 1, and we have zeros at minus 9, positive 6, and 0, which is given by C. 71 asks us to do some synthetic division to carry out this quotient here. Let's remember that to do synthetic division, we need to know, first of all, what is the root of this term? X plus 2 has a root at minus 2, because minus 2 would make this 0. And that's what we want to put in this little box here. We also want to encode the coefficients, and we want to take extra care not to miss coefficients of 0 that are given to terms that don't appear in the polynomial. So for example, there's no x's here. That needs to get recorded. So we have 1x cubed, we have negative 1 for our x squared coefficient, we have a 0 for our x to the 1 coefficient, and our constant coefficient is 4. So we encode those constants, and then we do the following algorithm. Dropping the first coefficient down, I multiply it by the root, and I put it here. Then I add these two together, and I repeat. Multiplying by the root, we get 6. Adding them together, still 6. Multiplying by the root, negative 12. And then adding them together, we get negative 8. Now, this lets us take these new numbers and encode our answer. If this is an x to the third term, dividing by a degree 1 polynomial brings us to an x squared term. So this will drop down by 1. And then this becomes our first power term, this our constant term, and this is our remainder of -8. So we're going to want to put that over here in the numerator and keep the original divisor in the denominator, which is given to us here by answer A. Question 72 asks us to do the same thing. So we begin by identifying the root of +5, putting it here. We encode the coefficients. There's no skips this time, so we don't need any zeros. We drop the first one down and begin our algorithm, multiplying by 5, adding these together, multiplying by 5, and so on. We keep doing that algorithm until we get to the end. We note here that we have a 0 for a remainder, meaning this x minus 5 was actually a factor of the numerator polynomial here. And noting that we went from x to the 4th power to x to the 3rd, we write down this descending sequence of coefficients, and our remainder of 0 means there's just no quotient left over term here. There is no remainder. And so we have this clean polynomial as our quotient, which is given right here. Question number 73 asks us for all the rational zeros. I believe we're backing away from the rational zeros theorem, but just to wit, if we're given a polynomial like 73, we have only to look at the constant and the leading coefficients to figure out what rational zeros are possible. The possible zeros will be fractions composed of factors of the final coefficient, the constant coefficient, over factors of the leading coefficient. So the factors of 5 are 5 and 1. The factors of 6 are 1, 2, 3, and 6. So those will be my denominators here, 1, 2, 3, and 6. And we need to fill out factors of 5, or 1 and 5, on the top of each one. So that gives us the following options, and we need to include the positive and negative versions of each. Now, one of the reasons this is kind of being phased out in favor of the graphing method is that's a lot of work, possibly, just to check for rational zeros that may or may not be present. Not all polynomials factor over the integers, and so not all roots are rational. So we wind up with 8 times 2, that's 16 possible rational zeros to check, or you grab your handy-dandy graphing calculator, you type this into your y equals line, and you just check to see if there are any obvious roots, because we don't need many to factor this down to a quadratic and then factor it the rest of the way. If I type that into a graph, I wind up with -1 being a possible root. So hey, if you start at the beginning of this list, I guess it wouldn't take you long to find that. And if we then synthetically divide by that root at -1, we get a remainder of 0. We should, if this is indeed a 0, which corresponds to factors. And then we get this other polynomial, 6x squared plus 13x minus 5, as the other factor. So that's the first factorization of this. Now we want to factor this again. And we can do that in a variety of ways, but using the AC method, for example, we could factor this as 2x plus 5 times 3x minus 1. And setting these each equal to 0, we find our remaining rational roots for f of x. This is given by answer D. We continue. Question 74 asks us to solve this equation in the real number system. Okay, well, it's a polynomial set equal to 0, so perhaps we should try to factor it. We might take note that the rational zeros are only possibly plus and minus 1, plus and minus 7, plus and minus 1/3, plus and minus 7/3. That's factors of 7 over factors of 3 in all combinations. But we could also look at a graph, and looking at the graph of this function, we see that there is this 0 in between 0 and 1. You might be tempted by the plus and minus 7/3 here, but we could carefully note that these are actually closer to 3 than they are to 2. And so 7/3, which is 2 1/3, is probably not what these are. But you could try them, and you would find that you can't synthetically divide by them and get 0 remainder, but you can synthetically divide by 1/3 and get a 0 remainder. If we do that, if we put 1/3 in here as our root, positive 1/3, and we try that synthetic division, we're going to find that it is indeed a factor. We get 0 remainder, and the cofactor, the other polynomial, is going to be 3x squared minus 21. Solving that equation, we could just use the square root property to get x is equal to plus and minus the square root of 7. And these are the answers given by B. A little bit of metagaming work here. This is a multiple choice test, right? So it's going to be one of these, and none of them say no solution. So as far as our synthetic division is concerned, we have 4 good options right here. 1/3, 3, negative 1/3, and 3. And if I quickly compared the graph that we had with the available answers, the available rational roots, we could see that 1/3 must be the correct decision about what we should do, and really get this answer without having to go through the rest of the process at all. So, just a little shortcut there, but the full workout is given. Question 75 asks us to find the domain of a rational function. Rational functions are quotients of polynomials, and quotients only have one real domain restriction, which is that their denominators can't be 0. So really this question comes down to, what's the denominator and where is it 0? We need to leave those points out. So we set the denominator equal to 0 to find those forbidden values, which we can do by factoring, and getting x is equal to negative 12 and 3. So I want the domain to be all the x's such that x is not equal to those forbidden values. And that's answer A. Question 76 is asking for our vertical asymptotes. Let's do a little quick review of asymptotics here for rational functions. If you have a uncanceled 0 in the denominator, you're going to have a vertical asymptote there. And if you have a fully canceled 0, then you're going to, if you have a fully canceled 0 in the denominator, you're going to wind up with a hole in the graph at that point. There won't be an asymptote, but there will be a blank. And for horizontal asymptotes, or the long-term behavior of rational functions, we have only to look at the leading terms of the top and bottom polynomial. If the numerator polynomial has a leading term ax to the n, and the denominator polynomial has a leading term bx to the m, we need to compare n and m. If n is greater than m, there's no horizontal asymptote. This thing will have a different behavior in the long term than a tending towards a single number. If n is less than m, eventually the denominator is much bigger than the numerator, and we get a horizontal asymptote at y equals 0. So it'll tend towards 0 in the long term, positive infinity and negative infinity. On the other hand, if they are equal to each other, eventually this ratio is all that matters, and the lesser order terms do not really contribute. And so what we wind up with is a ratio of a over b as our horizontal asymptote. The rational function will tend towards this value, a over b, in the long term, positive or negative. All right, so let's take that back to these questions. The first one says, what is the vertical asymptote? Well, we have a factor in the bottom of x plus 9, and there's no corresponding x plus 9 on top. That means this is an uncanceled 0, and we will have a vertical asymptote where the denominator is 0. That occurs at x minus 9, and so that's answer A. For these two are asked for horizontal asymptotes. Well, to do that, we look at the leading coefficients. These have matching degree, and so we'll get a horizontal asymptote at y equals the ratio of their coefficients, which is answer B. Here, we have a polynomial whose degree on the top is smaller than the degree on the bottom. And this means eventually the bottom will dominate and give us a long-term tendency towards 0, which is what we have here for our horizontal asymptote. To graph this function, it's helpful to note at least two qualities of it. We could notice it has a horizontal asymptote. These have matching degree, so it'll have a horizontal asymptote at the ratio of their coefficients of the leading terms. That's 2 over 1, or y equals 2. We might notice that it has a y-intercept of 0. If I plug in 0, I get 0 over minus 4, which is just 0 again. So we know where this thing hits the y-axis. And we also have a vertical asymptote at the value of x is equal to positive 4. So what I might do is make a quick sketch of that, right? I might say to myself, okay, well, this is going to have a vertical asymptote at 4. This is going to have a horizontal asymptote at 2. And we know it goes through 0, 0. But we don't really know if it goes through 0, 0 like this, or if it's going to go through 0, 0 in some stranger way. But actually, we kind of do, because we know that this thing tends to the value of 2 in the long run, so it actually has to hug along this 2 over here. And the multiplicity of this 0 at 0 is 1, because this exponent of the numerator is 1. That factor, having multiplicity 1, means we cross our 0 at that point and go on to the other side. Now, the vertical asymptote isn't crossable. It's undefined at that point, so it kind of hits it and swerves down. And since this one has multiplicity 1 as well, both of these terms here have multiplicity 1. It is a split asymptote and will come down from above this time and then hug towards 2. So we can actually just use just this information and a little bit about multiplicities to completely sketch this graph, and that lets us, hunt a little bit more easily for the matching version of this graph, which is actually on the next page here. This note about multiplicities and what direction the asymptote goes in is great and all, but it wasn't even really necessary here because the sort of intersection of our horizontal and vertical asymptotes really told us everything we needed to pick this out from a multiple choice selection. Question 80 is asking us about a polynomial inequality. To solve an inequality like this, a sketch is really helpful. We note that this is an upward-facing parabola. We could find its zeros in the following way. And this question is asking us, when is it negative? When is it below the x-axis here, right? When is the y value negative? And we can see that's between these 2 points. Another way that we can proceed, though, is by finding these zeros and marking those on a number line themselves, and then by plugging in some values. We might note that by plugging in large values for s, we could make both these terms positive, and so this part over here will be positive. Each one of these has multiplicity 1, and so it changes sign across each one of these zeros. That gives us the following values of positive, negative, and positive between as we go down this number line. Now, the question is asking, where is it negative? And so that's here between these two values, which is the same as the conclusion we arrived at from our sketch of the graph. That is answer C and is marked on a number line in this way. Question 81 is very similar, except now it's asking us, where is this polynomial positive? Again, we could take both an analytic or graphical approach to this, but let's just start by saying, well, where is this polynomial equal to 0? That is germane to the question, and we can find that by factoring. So when we do that, we get these two values of 2 and 3, right? And we could plug in some test values to determine whether we are positive or negative between these two. For very large values of v, these are both positive, and so this term will be positive. 3 has a multiplicity of 1, so it changes sign here, and 2 has a multiplicity of 1, so it changes sign again. We might also sketch this polynomial. We note it's upward facing with these zeros, and so it has to look something like this. And then if we ask the question, where is it positive or equal to 0, we get these two branches as our answers. And that's what they've marked here with the following interval notation. 82 asks for something very similar, but now they've even given it to us in a factored form with these multiplicities listed. So we notice that we have these two critical values where we could possibly change sign, -3 and -1, which we want to put on the number line like this. Now notice if x is larger than -1, both these terms will be positive, and so this will be overall positive. The factor corresponding to the -1 root here has a multiplicity of 1, and so it changes sign. But here, at the factor corresponding to the 0 of -3, it has a multiplicity of 2. And so it's actually going to keep its sign. It's 0 at this point, but it's negative on either side of it. But we were asked to find the positives. So that's only this branch over here and not including -1, which we could mark in this way, moving on. The following questions pertain to using either the compound or continuously compounded interest formulas. What we're going to want to do is be able to encode what are R, N, P, A, and T in terms of the question and what they want us to figure out. They've told us that a certain amount of money, that's our P, is invested at a certain rate, that's our R, written as a decimal, and with a compounding schedule which happens a certain number of times per year. Here they say it's semi-annually, which means that our N, or number of times we compound per year, is equal to 2. We might also have things like quarterly, which is 4 times a year, annually, which is once a year, monthly is 12, and so on. We're going to have a period of 9 years, so we know our T is equal to 9. And really all we have to do at this point, because they're asking us for the amount in the account, it's already solved for the amount in the account after 9 years. We just plug those values in and evaluate this in our calculator, rounding to this as appropriate. That's our answer. Question 84 is similar in that it is asking for the balance in the account, or asking for A. They've given us P, they've given us R, and they've told us it's continuously compounded, which means we use this formula instead, which really only has the parameters P and R and the variable T in it. So plugging in what they told us, 5,000.056 for our rate and 3 for our t, we wind up with this number here. That's the amount in the account, which is answer D. Now, on the other hand, this one asks us for something a little different. It gives us the amount in the account after a few years. It tells us how much we put in initially, and it tells us how long it was in there for. What we don't know is the rate. So if we plug in everything we know into this equation, what we see is that r is the thing I have to solve for. What we want to first do is isolate the exponential, and then in order to get something out of the exponential exponent, we need to take the log of both sides, which will cancel this e to the power of. We take the ln, that's the log base e, or the natural log of both sides, and we get this following line. Now, next, we just want to get rid of the 8. It's timesing the r, so we divide by that over here. You could also just divide by that at the end here, and that gives us a r of 0.0300 and so on. That's approximately 3%. That's the answer they give for A. Moving on. 86 asks us for the log base 8 of 32. We want to remember our change of form property. Log base b of x equal to y has a companion fact, which we can go back and forth from, which is its exponential form. That says that b raised to the power of y must be equal to x. So what we can do is actually rewrite this in its exponential form, and then note that both 8 and 32 are powers of 2. This is 2 to the third, and this is 2 to the fifth. So we have 2 to the 3x equal to 2 to the 5. Now, taking log base 2 of both sides, or just comparing the arguments of the two exponents, we have that 3x is equal to 5, and so x must be equal to 5/3. That's answer D here. Question 87 asks us to expand this logarithm. We need the following rules to do that. We need to note that the product within a logarithm can become the sum between two logarithms. Likewise, a quotient will become a difference, and powers inside of a logarithm will become the product of that exponent times the logarithm of the base. So doing that here, we could expand it in the following way. X squared is on top, so we're going to wind up with a 2 log base 4 of x as a term. We are dividing, so there'll be a minus sign. And then y to the 6th power, well, we could pull the y out front and instead take log base 4 of y. And that's our expanded version of this. Same thing with question 88. Factors in the numerator will be positive terms out here. Their exponents will become their coefficients, and we will subtract log base 2 of 4. So you could actually get this evaluated as a number and not just leave it as log base 2 of 4. It evaluates to 2. So that makes D the answer here. 89 wants us to do the opposite somewhat. They want us to contract this into a single logarithm, which is an important step for solving logarithmic equations. What we notice is that we have addition, so that's going to turn into multiplication between two terms. We have a 3 times this, so we're going to wind up with its argument, x, being raised to the 3rd power. And here we have x minus 6, that's going to get raised to the 5th power, and then we multiply those two together. That's answer C. Moving on. The next 4 questions ask us to solve certain logarithmic or exponential equations. Question 90 says log base 4 of x plus 1 is equal to 3. In order to get rid of log base 4, we raise 4 to the power of each side. That composes the log base 4 with 4 to the power of and cancels them to give us x plus 1. Over on this side, I have 4 to the 3rd, which is 64. This tells us that x is 63. For 91, there's a little bit more work to do. Let's check it out. We start with the sum of logs, which we can write as the log of a product. Then, to get rid of log base 3, I raise 3 to the power of each side. This is going to give me the argument here, x times x minus 24 is equal to 3 to the 4th, which is 81. Now, if we expand this and regroup our like terms, we get a polynomial that we can actually factor. But unfortunately, we need to check both of these answers, both 27 and minus 3, to see if they are inside our domain. What do we mean by that? Well, if we're talking about the log in some base of x, we're implicitly talking about x's that are greater than 0. That's our domain restriction for logs. And that b, the base, is going to be some positive number which is not 1. But how could we see that minus 3 wouldn't work? Well, if I go back to the original equation and I plug in 27, I get positives for both my arguments. If I plug in minus 3, however, I get a negative inside of this logarithm, which we're not going to allow inside this course. It's going to be part of a domain restriction. So we have to throw out this value. It's very important when we do logarithmic equations, square root equations, and rational equations that we check to make sure none of our answers actually fall outside of our domain like this. 92 is very similar. We want to first combine the logs on the left-hand side. And since this is the common log of 10, we want to raise 10 to the power of each side to cancel. Here we have a rational equation, so we have to be careful about not dividing by 0 here. But we can still solve it by clearing denominators, multiplying on both sides by x minus 3, then distributing, grouping our like terms, and solving this linear equation. That gives us x is 5, which has no trouble in any logarithm and isn't a denominator zeroer of this particular rational function, so this is going to be our solution. Question 93 is an exponential equation. Instead, we have 2 to the power of something is equal to 1 over 16. Now, some of these we're going to need logs in order to free up that argument, but for this one, we can actually just get a common base for each one. Our common base is going to be a 2 because 1/16 is 2 to the power of -4. Negative to put the 16 on the bottom and 4 to give us a 16. Now we can equate the arguments, essentially taking log base 2 on both sides, and we get 5 minus 3x is equal to -4. Grouping our like terms and dividing off the coefficient, we have that x is equal to 3. Question 94 is asking us to rewrite this exponential expression in its logarithmic form. We recall that any exponential equation can be rewritten as a logarithmic equation and vice versa in the following way. We take our base, we make that the base of the logarithm, and we interchange the role of x and y here. If this was the output, we make it the argument of log. If this was the input of the exponential, it's the output of the logarithm. So for number 94, we have e to the x equals 6. This tells me that x is equal to the ln of 6. Alternatively, we could see this as taking the natural log of both sides, which would cancel with e to the power of to just give me x, and accrue to give me an ln of x on this side. 95 is a question about the domain of a logarithm. The domains of logarithms are precisely those values for which the argument is positive. It can't even be 0, it can't be negative, it's got to be positive. So this is the set of all x's such that x plus 5 is a positive. Solving this rather simple inequality, we have that x must be greater than -5, and that gives us the following interval as our domain. Question 96 wants us to solve this equation. This exponential equation we cannot evaluate using our like bases trick because there's no nice way to write e in terms of 7. Instead, what we want to do is take the log of both sides. If we take the log of this side, we get ln of 7. If we take the log of this side, base e, we get x plus 5. This lets us solve for x by just minusing 5 over, and ln of 7 is the exact value. If we wanted to plug this into the calculator, we could get some approximate value out to decimals, but actually the exact value is what they are looking for here. Question 97 brings us back to compound interest. They tell us that it's compounded continuously, and we're going to select the equation for that reason. It tells us that we have an interest rate of 5.75%, so we know the value of r, and it asks us how long it takes for an investment to double in value. To double in value means that the current amount is twice the amount you started with. And actually, that's enough information, because if we know the amount in terms of p, that is to say it's 2p, I could cancel p from both sides without ever knowing what it was. Thus, the doubling time is actually independent of the amount that you start with. Now, r has to be rewritten as a decimal, and what we're asked here is what is the value of t? What is the value of time for which we will have twice as much in the account as we started with? So to find that, we need to take the ln of both sides. Taking the ln of 2 here, we get 0.0575 t on the other side, and solving for t just means dividing that coefficient to the other side. We could plug this into the calculator to get an approximate value, and round it to whatever decimal places we like. Here's the answer out to 3 decimal places. Question 98 is asking us to take a look at this model. We have a certain amount, which would be pounds of radioactive material, is given by the initial amount times e to the power of -0.00866x, and they are asking us how many pounds will be left after 110 years if we start with 600 pounds. So this tells us our A naught, this tells us our T, and actually they're just looking for A here. So this is going to become an evaluation problem because we're already solved for the unknown thing that they're asking for. We just have to plug in the numbers and see what we get. Rounding to the whole number of years, rounding to the whole number of pounds, that's going to be 231 pounds. For number 99, they're asking us how much must be put into an account to get $25,000 after 4 years if it is 9% compounded semi-annually. This tells us we're looking at the first equation, that it's compounded semi-annually, with an n equals 2. And what we're being asked for is to solve for p. So we might notice that there's this big expression here. We really just have to divide that away from p in order to find out what p is. So that's 25,000 divided by this term, 1 plus 0.09 over 2 to the 8th power. This gives us the following amount, which is answer C. Finally, last question, it says, what principal, so this is the question, must be invested at a rate of 6%, or r equals 0.06. If we're compounded continuously, we're choosing the equation, and we want $1,500 to be in the account after these 3 years. So how do we do that? Well, we want 1,500 to go where our A goes. We're solving for P, and we have e to the r as e to the 0.06 times 3. So we're going to take and solve for P by evaluating this argument for e to the power of. That's going to be 0.06 times 3 is 0.18. And then if we just divide that to the other side, we have 1,500 divided by e to the power of 0.18 is our P. Evaluating that in the calculator, we get the following 1,252.91, which is answer C. Alrighty, that's going to do it for this video. Thank you very much for your patience. Have a great day. Good luck with your studies, and I'll see you in the next class.